I'm so excited to be here. Had an undergrad from Berkeley before moving to Princeton as a grad student, so I love California. It's always good to be home. And I would like to talk about using artificial intelligence to discover new rules of our universe. But I just want to first of all thank all the students and postdocs and collaborators I work with, because these are the work they actually have been doing. And I want to point out especially my students at Princeton, Kimberly Stachenfield, DeepMind research scientist, postdocs, Pablo Lemos, now Jeffrey. There's just a lot of people that I work with, and I have to show some pictures so that if you see them around, you should be pretty happy to say, I heard about your work. That's pretty cool stuff. I hope that I won't disappoint you too much. So artificial intelligence. Ooh, we can't see the words, maybe. Can we see the words? No, we cannot see the words somehow. Somehow it doesn't show up on the slides, but artificial intelligence to discover new rules of the universe, or the non-clickbait version, which now I have to remind myself what I wrote, is to use deep learning or neural networks to provide new pathways to scientific discovery. That basically non-visible, invisible words that doesn't show up. It's even more mysterious than I expected. I don't know if there's a way to fix it in the back. Oh, it's showing up in a small screen. That's good, so I don't have to remind myself what I wrote. So for those who don't do this, for those who are doing astrobiology or other things, like what is a neural network? OpenAI's founder said a neural network is a digital brain that lives inside a computer. So as a professor, you said, OK, I have to make a digital brain that lives inside a computer and a slide for the talk tomorrow. We're making the slide last night on the flight over, so what do? I created something like this, actually not me. I typed into a machine, and it's called DALL-E, and said a neural network is a digital brain that lives inside a computer, and it generates, this neural network generated image is automatically out. So I don't have to make my slides anymore. Makes my life very easy. Next thing, well, neural networks also can write its own code, or the clickbait version that you have heard, artificial intelligence can reproduce itself. It's like sentient. Well, it is true the top version. Depending how you interpret the lower version, it means different things. It is Copilot running in Visual Studio Code. I use it myself. If you type something like, for the astronomers, if you type get Sloan RAN deck, it will show up with the code. It's pretty awesome. This one is like calculate runtime in seconds, and it pops out the code for you. This is already writing about, they claim 40% of the code on GitHub right now. I've not checked this. This is definitely on Vice.com. But Copilot is working, and I and myself and some of my students actually use it. So these are just some couple recent examples, other than self-driving car, landing drones, and all the stuff you probably heard, that happened within a deep learning community. But these are all like last 6 months' work. So you can see how fast things are changing. But the scientific community, I think 50 to 90% of the scientific community believes machine learning can only do things, with these following things. They can help you. Accelerating simulations that already know how to generate with our known physics. Validating something that's normal or abnormal according to our rules that we already know. Do what we can do just according to our understanding, because we're programming to it, right? We're explaining to it. We provided data, but faster. So that's what I think most of the scientific community are thinking about, that machine learning can do, and these are the people who don't hate machine learning. So there's another chunk who don't want to do any machine learning, neural network, artificial intelligence, depending how you use those words. And I think we have done some of these ourselves. On the left-hand side, I'm going to show you a cosmological simulations. Cosmology means the universe. About these dark matter particles floating around, and they interact with gravity. And here, I think it's about 1.3 billion years old of the universe. It's a very small chunk of the universe. And these dark matter particles interact with each other. So what is dark matter? Anyone knows what dark matter is? Ooh, OK, we have one hand up. Dark matter is what we think. It's also true because Marvel Universe mentioned it in the Thor movie, by the way. But joking aside, it is also true that scientists think 25% of the universe is made of these dark matter. 5% of it made out of stuff that make you and me, baryons. And there's 70% of it called dark energy that we don't know anything about. So here's a simulation that basically tries to encapsulate what we know about the universe and simulate it forward. And we are able to accelerate this cosmological, just the dark matter part, simulation 1,000,000 times faster. So we thought that was pretty cool. On the right side is a bit more nerdy slide in case there's some people who want to see slides with plots in, showing the error bar of our neural network predictions on the left, the unit displacement view. On the right is sort of like a benchmark, the fastest simulations that you can run, and basically 10 times better and a lot faster. And then we also go one step further because we only observe things that we know and love, like the galaxies and stars and planets that you guys also want to find, right? And to go from the dark matter to the galaxy properties, these simulations take, say, 1,000th of the universe will take about 100 million CPU hours to run. And that's not even that correct, according to them. So we want to accelerate it, and we also did accelerate using something called graph neural network, which I won't go into details, but that's something that a lot of people might have heard of. You do machine learning. That's extremely useful when you have very unstructured data. And I'll use it later because our planets are very unstructured. It's like these graphs composed of nodes and edges connecting the two nodes together, and it's great for describing basically bodies interacting with each other, which physicists love. So we do all these cool things, but I would claim that 90% or more of scientific community believes machine learning or neural network or AI cannot discover new rules that we humans have not yet discovered. Okay, so that's what we think right now. I think most of us will think that's probably true. I believe we can, fingers crossed, in the near future. Not right now yet, in the near future. And I'll show you pathways we have made in that direction. So we look up in the sky. Let's think as an astronomer, so Newton back in the 17th century. Oh, forgot which century that was. Can we predict what happened and infer from what we have seen, right? Can we infer the rules? So time t0 on the left, time t1, it moves a little bit more. What do? Traditionally, we stare and stare and stare at the sky. Think of these as planets. And then maybe you got hit by the apple tree. This is the famed apple tree in supposedly his manner. So you have to be rich. Someone brings you food when you're thinking about all the science, and have nothing else to do, better to do, or people spend time with, and you got really lucky, and then you discover Newton's law. And works really hard, I'm sure. But then maybe I won't want to do all that, and I just want to do something slightly easier. I use something called symbolic regression. It's part of these algorithms people have been using in genetic programming and evolutionary programming, which I'm not going to talk all about. But the idea is that we have a bunch of mathematical functions and parameters, and we form new equations, and then do this huge search and find the correct equation for a better fit of the observations. So it's just a huge search tree. People have done it before, but it's really hard to do it because it has a huge search space. So it becomes like a Google search question, because you can form billions of equations with just not that many parameters and functions. So what do we do that's different that makes it possible to claim that you can discover new rules using machine learning? So what we're doing today, which I'm going to describe to you, is to combine artificial intelligence, this neural network that you heard about, that creates my slides and writes my code, and symbolic regression together to extract new rules or existing rules about a system. So how do we do that? On the left-hand side for you, it is this data set. And I'll use neural network. In this case, I use this graph neural network that I slightly talked about before to make sense of the system. For the scientists and nerdy people like me, you can think of it as dimensionality reduction, using neural network as a tool to crystallize the knowledge, to make sure that it can predict the system what it's going to do forward in time. And then on the right-hand side is somehow we can extract this equation by combining what the neural network has learned and then just search. Right? But you can't search a whole space because it's so large. It's neural network, you heard, 3 billion parameters. But now we're going to search a much smaller space because of what we did in this work. And I'll show you what we did. All right, but first, before we talk about all this grand stuff, we need to make sure this graph neural network that most of you might not have heard of, is quite new, is able to predict the dynamics properly. So let's see if we can do that. Here is some results. Ooh, if it plays. So outcome is a 1,000-step rollout of the true on the top and the predicted in the bottom. And you have 3 different scenarios: the n-body, the balls bouncing in the four walls, of strings falling on the masses. And here's our result. Let's see if they're OK. The balls bouncing the four walls definitely don't do very well, but it's a very chaotic system. It turns out super hard. And then we can try that again and see if you. But then n-body system did pretty well. The strings is pretty good. And you're like, OK, the neural net can do something we already know, right? So that's still cool. You want to make sure they do what you expect it to do. Then we do something slightly different, which is making the neural network predict something it hasn't seen before. It has not seen n-bodies with that many planets. It has not seen that many balls bouncing in four walls. It has not seen such a long string. So we have trained the network to learn from sort of doing multiple different tasks to doing a task it hasn't seen before. But we did not use transfer learning, by the way. So for those who are aficionado in machine learning, we did not use transfer learning techniques, technically speaking, and see how well we did. Not too bad, right? Given that neural network hasn't seen something like this before. It's like taking a baby to the street and say, like, figure out how to get home. It works. So now we can predict the dynamics using this graph neural network, which I described here with a bunch of nodes and edges. Edges can be used to describe interactions. Nodes are describing the bodies, attributes of the bodies that you can be events, can be the planets. So early on in COVID, I actually used this graph network to model transmission and rates of COVID in different cities, and how it basically goes from different places, looking at the number of people actually moved using cell phone data. So you can also do many things with graph network. You can model chemistry data set. Of course, there's a lot of molecules. There's many things you can do. So now, if you believe me that we can predict the dynamics, this network is able to do what it claims to do, to predict dynamics of a system. Then we do something a little harder. This is the harder slide I will show you guys. And we have the neural network to make the predictions and basically make really good predictions now. But when you're training the neural network, you actually want to apply something called L1 regularization. What it really means is that I want very few elements. So instead of like a billion weights, you want to have a few, very, very few weights. And what does that mean? It means that if you have very few parameters that's needed to characterize this network, then you have a shot in understanding the network. Okay, so easy ways to think about it is this network can be boiled down to very few parameters. And once you can do that, you can regress to find equations and sort of understand your network. If your network can be described by several equations, I think you can understand it. So what happened is that there's some more words on it. Given the input simulation, one of them is a 2D. We do not expect dimension of these edge parameters to be more than 2 originally. Though we find that if we set and force it to only have 2 elements in this edge function, it actually doesn't run as fast, and it doesn't train as fast, it doesn't perform as well. But then we use something called the L1 regularization, which basically just reduces the number of elements in the edge function that are important to fit these observables. And then we put the edge element through this symbolic regression, this huge search tree of the equations, and you see what we fit for the 2 elements. And it seems to be working pretty well. And we found the force laws from observed system, which is Spring's law in 2D, and 1 over R square law in 3D, which is the Newton's law that you guys have seen before. So we thought, OK, this is for first paper that ever combined neural network and sort of genetic programming. I think that was pretty cool. And we recover Newton's law. But then how about using some real data? Like all that stuff, we knew what the answer was. We knew the data. We generated it. It feels very easy. So what do? We took the NASA Horizons Ephemeris data, so all the orbits of 31 bodies, moons and planets, all together. And then we feed it to the neural network, just like what I described before. What happened? Well, it works. A, recovered the Newton's law. Hold on to questions about Newton's law versus GR. B, it learned all the masses of the moons and the planets, which is pretty cool, because all it got is positions of these planets and moons over time for 30 years. And we feed it to a network that didn't know Newton's law, didn't exactly know geometry, right? So in that sense, it's a pretty cool accomplishment. And I'm going to show you a YouTube video that my student, Miles Kramer, made, if it plays. and doesn't show us any ad, thanks to Google. So the true is this is showing the inner solar system. The true is the mesh one. The solid one is the predictions. I'm showing 3 different ones here, and I'm going to describe what these 3 things are. And they will go slowly, one by one. And you see that each one of them actually perform differently. This one has a huge error bar. You can see the differences and this differences. And this one actually maintains pretty well. Graph neural network, which is what I described to you before using these nodes and edges. And you can see that if you just use neural network, there's quite a bit errors. It's already starting to be different. We only used about 24, I think, years of data, and we have to predict the last 6. So to show what happened the last 6 years of the inner solar system. And you see there are a bunch of error bars, and you're like, OK, that's not so good. Then what we did is that we took what the network has learned, do this L1 regularization, reduce the number of elements in the network and the parameters that's needed to make the system predict correctly. And this is what the equations was found. And we use those equations to evolve forward our predictions. The error bar is smaller. So this time it's using equations found by the network and just evolve forward from the initial conditions of planets. Here is a 3rd step, which is a combination of genetic programming and neural network, where you took the learned equations by this genetic programming, after reading what the network has learned, feed it back into the network, this edge function that we replace it with Newton's law, basically. What Newton's law that it found, that's what happens. And the network can predict very, very accurately. And don't look at all the other things. So how about discovering new rules, as I promised in the last few things? I want to show, again, the cosmological simulations again. We look at this, and one of our referees said, how about discovering something new? We've discovered Newton's law and rediscovered Newton's law. By the way, it's very hard to discover GR. I can talk more about this if you ask me questions about it later. We tried. It's not for lack of trying. And so we have these dark matter simulations zooming around. This takes 100 million CPU hour simulations. We're able to accelerate, blah, blah, blah. But we want to learn something different about this. And you can see that there are these clusters forming. Think of it as cosmopolitan cities like New York or Los Angeles of dark matter. They all live together, and they like to crowd together. So I want to ask myself something I don't know, and no one knows because we haven't thought about it before. What is the density of dark matter within the center of these dark matter halos? So imagine you're asking about the population density of New York City. Oh, sorry, I'm still living in New York now, I know. And the central density of New York City of population, but just using the surrounding suburbs population. So this is what I'm asking the cosmology question, which is the central density of dark matter halo given the surrounding halo, the surrounding little densities of cosmopolitan or not so cosmopolitan towns. We can make guesses of what this answer may be like, but we do not know this analytical formula ahead of time, and I just don't know. Maybe I'm not a very good theorist, that might be a possibility. But it's just no one knows. So we did what we just described, right? So we took the dark matter particles and find all these cosmopolitan cities of dark matter, and then you fit it to a neural network. This neural network, and then you use this graph neural network to understand, make predictions about the central density of dark matter halo, which no one knows what those unknown dark matter density equations should be like. And we extract an equation out of this. And let me show you the comparisons of different sort of intuitive equations that we have versus what the network has found. So I know this is the boring slide, but I'm just going to point you to 2 things that's important. Here are what we guess is happening. Here's the error. So larger is bad, smaller is good. And this is the best guess we can make as a scientist, just because that's what we can come up with. And all these coefficients and stuff like that, and it's summing over all the different stuff around it within certain radius. And the best with math, which is allowing it to use all the information just like humans are allowed to, it actually got a much better error than what we can do with human intuitions. So it got us pretty encouraged. So what is this next frontier, right? So you just saw AI can learn a bunch of different things. It can learn unknown rules and fitting formula. It can learn the known ones, which is good, but it can also learn something unknown. And by the way, the theorists haven't figured out why those formulas are correct, and I don't know yet. That's the next thing we have to do. a physics equation has typically like 3 to 10 variables and works in a specified range of scales. Think Boltzmann equations, think Newton's law. They work in certain scales in certain scenario. It doesn't work in all scales, right? But after studying them for many years of these 5 variables or 10 or 3, scientists develop an intuition what these variables mean, like force, velocity, pressure, temperature. They mean something. We transfer our learning to other scenarios, other problems. Like now when you say force, you see force in many different things. And it's not by chance that any fitting formula of 100 to 1,000 variables, on the other hand, works super well in this neural network situation to fit a field of 10 million variables, these huge simulations. But it will be hard to stare at these 100, 1,000 variables to develop any intuition. Yet it doesn't mean these fitting formulas are not containing any knowledge that can be coarse-grained to extract intuitive structures. Just like how we transfer the notion of force in Newton's law to all kinds of different problems, can we do the same transfer to give us better understanding when we stare at these fitting formulas? So there's a lot to understand, from fitting formula to understanding. But that's why this is a huge important step and challenge. I'll invite you guys to join us. Thanks.